Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Great. And without further ado, I'd like to introduce the first speaker, Carlos Gestrin, and he'll be talking about machine learning for big data in the cloud.
Thank you. What a thrill to be here. There's lots of really cool faces and new people working on machine learning. This is really, really exciting. Exciting to also be in the Seattle area. And I'm going to be talking about really work of my students, Yucheng Lo and Joey Gonzalez, who are here. You should stand up. Apo Kirula, Jay Gu, and my postdoc, Danny Bixen. And so let me also introduce other people from my group, new people. So Svilen, it's a new postdoc. Tyler, new graduate student, and Shingo, a visitor from Sony. So you can hang out with them, and they've been working on related things too. And the work that we've been doing is on GraphLab, a system for large-scale machine learning on big data. And the question of big data is pretty obvious these days. We're all familiar with it. And my issue with it is well characterized by this article in the New York Times from a couple of months ago, where they said that data has become an economic asset like currency or gold. And I don't know if I believe that is true. I think it is only true if we don't just store data, but if we get some value out of it, if we do some interesting process. And I think this is where machine learning comes in. And so part of the reason that we're here is to do machine learning on big data and extract some really deep understanding. And we have to do that in the context of new computer architectures. And people like me who have been programming machine learning for a while, or if I'm honest, really my graduate students, are not so familiar with the ins and outs of programming these large-scale parallel systems. And we end up with spending a lot of time on things like race conditions, distributing states, race conditions, communications, race conditions, and these are just things I don't really know what they're about. And we end up with code that nobody can use and nobody can maintain. And because of that, in our field, people have been moving to higher level abstractions for programming parallel machines. And MapReduce is one of the standard abstractions where Hadoop is a public domain implementation of that, or an open source implementation. And they're good for basically independent subproblems. So for example, if I have a large set of images and I want to extract faces on these images, I can independently send them to each processor. So if I have this large number of independent subproblems, MapReduce is quite good. And you can step back and say, OK, machine learning, things like feature extraction are well done with this kind of abstraction. But the question that we posed a few years ago is whether there's more to machine learning. What are the types of problems that don't break up so easily into this set of independent subproblems? And if I step back and think about machine learning, I think the power of machine learning is about discovering dependencies in data and discovering structure. And problems with graphs are characterize a lot of this structure in machine learning, and they're not well suited for MapReduce, in our opinion. So let me give a couple of very high-level examples of that. So let's say that I have a large database of personal images, and I label this image and this face as being my grandmother. And I want to propagate this information throughout this database of images. And what can happen is that there might be other images where my grandmother appears, but the similarity between this pair of images might not be strong enough to make a good prediction. And what graph-type algorithms can do is connect faces across different images that are similar. And also, for example, look at the fact that people who co-occur in an image with other people tend to be the same set of folks, so families co-occur together. And if somehow I propagate this information through this graph using graphical models or other standard techniques, I can make better predictions. So this is an example of a graph of dependencies where it's very hard to think about how to break this into independent subproblems. Let me give another example that we're very familiar with. This is collaborative filtering. So let's say that I want to make movie recommendations, and I have this user, and his favorite movie is Women on the Verge of a Nervous Breakdown, followed by The Celebration, City of God, and Wild Strawberries. And then you can step back and ask, what other movies should I recommend to this user? It might be hard to think about what to do, but there are other users who are similar, who have liked the same movies and maybe liked other related movies like La Dolce Vita. And you might say, oh, let me recommend La Dolce Vita to these users. And this idea of exploiting this graph of dependencies, maybe by doing collaborative filtering, matrix factorization, or other such techniques, is a way that we can extract, again, value from this data. And again, this is true for many machine learning problems. So for example, if you're modeling text data using topic modeling, for example, the LDA type models, then the graph that you're dealing with is documents and words. So these are the words that appear in each document, and you're using this graph to discover topics. So again, stepping back and thinking about the pipeline of machine learning, we might have a lot of data. Maybe these are images, maybe these are the documents. And typically, we do some initial pre-processing where we extract some features like faces, and we form a graph of them based on some dependencies, and that gets fed to some kind of structured machine learning algorithm, like graphical models, LDA, matrix factorization, and so on. And that gives us what I think about as the value of the data. And if I think about this pipeline, the first two steps on the pipeline, the first two blue boxes, what we call graph ingress, are well done with data parallel methods. Things like Hadoop and MapReduce are quite good at doing that kind of thing. But the purple box with structured machine learning is where it's hard, and this is where we'll be focusing our efforts on. So if we step back and think about what is there more to machine learning that does not fit into the Hadoop model so well, here's where I think about these problems that I've been mentioning, things like semi-supervised learning, collaborative filtering, graph analysis, and so on. And we call these graph parallel algorithms. And so let me give you a running example that we're going to use throughout the talk of a graph parallel algorithm. And this is the standard page rank example, which has been applied to many domains. But let's say that we think about it from the context of a social network. I wanted to figure out who to advertise to, and it depends on the rank of that user, the social rank. So I ask, what is the rank of this user? Well, it depends on the rank of the users who follow her. And what is the rank? Depends on the rank of the users who follow them. And you can imagine this is a loopy graph, and you somehow have to iterate this idea until convergence. And you basically say something like, my rank is the weighted average of my neighbor's ranks, my rank is the weighted average of my neighbor's ranks, and I iterate that formula until I reach some solution. So a lot of machine learning problems can be fit into this model. You have a graph of dependence, like the social network. You have some local function that you perform on it, like my rank is the weighted average of my neighbor's ranks, and I iterate that until I reach some convergent point. It turns out that from a theoretical and practical perspective, MapReduce is not a good abstraction for this problem. And this begs the need for what we call graph parallel abstractions. And that was the impetus of the start of the GraphLab project in our group. And the idea, or kind of the dream for us, was we come in, we know how to solve a problem in MATLAB on one machine. Somehow I'm going to magically give it to GraphLab and put it on, say, Amazon's EC2 cloud, and I get efficient parallel predictions. That's our goal. That's where we started. Now, this was, let me just give you a very quick overview of GraphLab 1, the first version that we started with. And you start with a graph, basically, for example, social network graph, where vertices have some data, for example, users' profiles, and edges have some information like similarity between users, and you want to perform some computation on this graph. So how do we compute on graphs? How do you think about that? We do it by thinking like a vertex. And how does a vertex think? Well, a vertex only gets to see itself and its neighbors. So if I'm the red vertex here, I can only read or modify data in neighboring edges and neighboring vertices. So let's go back to the page rank example. I get to read the current ranks of my neighbors. I get to update my rank as the weighted average of the neighbors' ranks. And if my rank has changed sufficiently, I get to tell my certain neighbors, oh, you should redo your computation. And this is the example of dynamic computations that you can do. So GraphLab is about writing simple programs like this, and then they get automatically parallelized for you. So they get pushed to the cloud, and all those other issues that you're worried about get addressed for you automatically. So let me give you an example of those issues. I mentioned race conditions in the beginning. So let's say that I'm executing these red vertices in parallel, and they get to modify data in their neighboring vertices. If at the same time the blue vertex gets executed, their scopes overlap. So they might modify data at the same time. And you don't know what happens with that. And when we started this project, people told me, oh, you're doing machine learning. These are all statistical methods. You should totally ignore this. You should just go and hope for the best. What they're telling me is that if you have no consistency, that you can have higher throughput. That's more updates per second. One way to think about this is, by the way, is if you have a big family and they're all sitting at this dinner table, if everybody talks and nobody listens to each other, you have more throughput. More people talk per second. But you might not really understand each other. So the same thing happens to many machine learning algorithms. So even though you can do more updates per second, you might have possibly slower conversions or even really bad behavior. So for example, if I show in this graph, this is Netflix data. On the x-axis, I'm showing the updates as they're happening over time. On the y-axis is a training error. And this is just 8 cores. This is not really a lot of potential conflict here, so small dinner table. If you have inconsistent updates, this is the kind of behavior that you get. So it doesn't converge, it oscillates, it can be quite problematic. While if you guarantee consistent updates, this is the kind of behavior that you get. Quickly converge to the right answer. And the nice thing is that if you're doing standard parallel programming, you have to deal with all these race conditions issues, but if you use GraphLab, you don't. GraphLab automatically takes care of this for you in a kind of user-tunable way, so you don't have to worry about these issues. So we've been working on this abstraction where you provide us with a graph and an update function, and you get to choose your consistency model, and it gets automatically parallelized for you. And at that point, this is about a year ago, a lot of algorithms were being implemented on top of GraphLab, and it was picked up in the industry quite a bit, and we're feeling pretty good about ourselves. So just to give an example, Tom Mitchell's group out of CMU wanted to solve a very large NLP type problem using an algorithm called CoEM, and they couldn't solve it on one machine, so they used Hadoop. And with 100 cores, they could solve the problem in about 7 hours. So they're feeling good, at least they could solve the problem. But then they tried out GraphLab, and with 32 EC2 machines, we can solve the problem in 80 seconds. That's about 0.3% of Hadoop time. So with this kind of result, we thought, OK, we're doing well. We're feeling good. Let's try something bigger. Let's try a problem where there was no published running time results. And this is a problem of about 7 billion edges, dealing with the Alta Vista web graph from 2002. And when we tried it, GraphLab failed miserably. It didn't work. And we have to step back and try to understand why did it not work? Why is it giving us bad performance? And the reason it was giving us bad performance is that these graphs are called natural graphs. Most graph abstractions, like GraphLab 1, Prego, and others, have assumed kind of idealized graphs. For example, graphs that have low vertex degrees, where they're easy to partition across machines. Natural graphs are not like that. They have many vertices with very high degrees, and they're very, very hard to partition. Just to give you a sense of this, if you look at the web graph that I mentioned, the top 1% of the vertices are touching 50% of the edges. And this is not just a problem on the web graph. If you think about a social network, you might have a very popular person who is connected to many others in the social network. In movie recommendations, you can have movies that lots of people watched. In machine learning, you have these things called hyperparameters that are connected to potentially every variable in the model. And if you're doing text analysis, you could have a very popular word that appears in many, many documents. And high-degree vertices can be problematic. So for example, if I try to partition them across machines, then I end up cutting a lot of edges. And the amount of communication I have to do is linear in the number of edges that you cut. And so this can be very bad. And in fact, for natural graphs, even if you could solve the NP-hard cutting problem, the cuts that you get would not be cheap. So even if you could solve the problem, you still have a ton of communication. And so understanding this issue of natural graphs led us to design GraphLab 2, where we thought we're introducing a new type of partitioning for our data, where we take these high-degree vertices, or vertices in general, and we split them across machines. And this type of partitioning is a natural consequence of the new abstraction that we're using. From the perspective of the user, you're still thinking like a vertex, you're still programming like on the left, but it gets executed in a new kind of distributed way on the right. And so just in 2 slides, I'll give you a sense of how things are different here. If we step back and look at things like PageRank and other machine learning problems, often when you're writing these update functions, it can be split into 3 phases. First, I gather some information about my neighbors, for example, their ranks. Then I change something about myself, like the weighted average of my neighbors' ranks. And then I go and I tell my neighbor something. For example, you should go and redo your computation. So this phase is where I gather information from my neighbors, I change something about myself, and I go back and tell my neighbor something, is a pretty general abstraction of what's happening in machine learning. So we define this gas decomposition, where you first gather information about your neighbors in a data parallel way. Then you change something about yourself in an apply phase, and then you scatter information in a data parallel sense with your neighbors. So this is our new abstraction. I'm going through it kind of quickly, but let me just tell you that a lot of the machine learning problems that we want to solve fall into this model. So things like inferencing graphical models, collaborative filtering, matrix factorization, clustering, and LDA can be expressed in this way. And since we're taking high-degree vertices or any vertices and splitting them across machines, the communication problem now is linear in the number of machines a vertex lives in. And this is called the vertex cut problem. And percolation theory suggests that it is possible to get low-cost vertex cuts in natural graphs. So unlike edge cuts, with vertex cuts, it is possible to do this well. And GraphLab 2 implements a number of online algorithms with some theoretical guarantees for implementing these types of cuts for the graphs that you read in. So this was a fast tour of GraphLab in our system, so of the GraphLab abstraction, but let me just reassure you, the GraphLab is an actual system that you can use. It's built on top of standard infrastructure for the cloud, like HDFS. It provides a bunch of functionality that you don't have to worry about because you can program in terms of the abstraction. So all the stuff that goes under it can be totally ignored. Or for those interested, you can use one of the toolboxes that we already provide on top of it. So for things like graph analysis, clustering, matrix factorization, and so on. So let me just give you a couple of examples of performance. One of the analysis problems that people want to do with large social networks is count the number of triangles. And a triangle is a three-way relationship that indicates that a person is part of a strong community. And if you look at the Twitter graph from 2010, there was about 38 billion triangles to be counted. And last year, there was a paper that used Hadoop for this problem. And this is the current state of the art for the system. And with about 1,000 machines, it took them 400 minutes to solve this problem in the Twitter 2010 graph. With GraphLab 2 and 64 machines, it takes us 1.5 minutes. Now, you can ask yourselves, is this because Hadoop is not implemented as well as GraphLab? That might be part of the issue, but the main issue here is that MapReduce is just the wrong abstraction for this problem. You end up with too much communication because of the issues that I mentioned earlier. Now, this is about going faster, a lot faster than Hadoop, but this might not be the only measure of productivity, especially if you're in industry. Another measure of productivity is programmer's time, or thinking time. So let me give you an example of that. Let's say I want to do LDA on Wikipedia, the whole of Wikipedia. This is the type of things that companies like Yahoo are very interested in because they want to use it for recommendations of content. And Alex Mola at Yahoo built this very cool system for doing very large-scale LDA. With about 100 machines, they can process 150 million tokens per second, which is very impressive. With GraphLab 2, with 64 machines, we can process about 110 million tokens per second. So it's pretty comparable. The difference is that the Yahoo system was built specifically for that task and took a long time to build. For the GraphLab system, Joey spent about 4 hours and wrote 200 lines of code. So this is a productivity difference. And finally, I mentioned this this Alta Vista web graph that was stomping us in the beginning, and now we can run it on something like 64 machines on Amazon with 1,000 cores and 4 terabytes of RAM, and we can do a whole iteration over the graph in 7 seconds. So that's 1 billion links processed per second. And there's only 30 lines of code that were written here. Good. So at this point, around this time, my student, Apo Kirola, walks into my office and says, "Buy me a Mac Mini." And I thought he wanted to watch TV. But he said, "No, I want to show you that we can solve web-scale problems on a small machine." And so there's always a genesis story for names of things that may or may not be true. A lot of cloud-based systems have animal mascots, like Hadoop has an elephant. So GraphLab is because I had a dog, a Labrador, so that's GraphLab. Apple said, I want to build the Graph Chihuahua, or Graph Chi. And by exploiting hard drives or SSDs, he can solve very large problems. And the challenge of using hard drives or SSDs is random accesses. So if your data lives randomly on the disk, and you have to read it from different parts of the disk, you end up spending a lot of time on reading and writing, on I/O. And what he has is a new parallel sliding windows method that minimizes the number of random accesses. And I won't have time to get into it, but let me show you a teaser of a result. If we go back to the triangle counting problem with Hadoop for 1,000 machines taking about 400 minutes, and GraphLab with 64 machines taking 1.5 minutes, with GraphG on just a Mac Mini, he can solve this problem in 59 minutes. And GraphG is our first endeavor on the next step for the GraphLab project, which is dealing with streaming data. So rather than a batch setting with all the data is available in one place, we can deal with data arriving and modifying the graph over time. So for example, on a Mac Mini, he can have 100,000 graph updates happening per second at the same time as he computes. There's 200,000 vertex computations per second. So the GraphLab project is about providing a novel system and a novel abstraction for programming large-scale machines, and it's really meant for some of the challenges that we face in machine learning. Our project is available under Apache 2 license, and at graphlab.org you can find releases of both GraphLab and GraphG. Thank you.
So we have time for a couple of brief questions.
Yes.
It's very interesting. The GAS abstraction we talked about seems sort of unsatisfying because the gather and the scatter seem redundant. Are there classes of problems for which you can just get rid of one or the other and do a random stochastic selection of vertices?
Oh, well, there's like 3 or 4 questions with that embedded various question. So let me just try to separate them. So the last question was, can you have a stochastic selection over vertices? Do you have to touch every neighbor every time? And the answer is clearly no. And so the way that we've looked at it is through some caching schema, you can just look at what vertices have changed. But you can also put in some randomization, which we haven't. But it's easily possible. The other question is whether gather is redundant with scatter. It turns out that for some algorithms, you want to broadcast information to your neighbors, and that's what scatter does. And for some algorithms, you want to aggregate information about your neighbors, and that's what gather does. And so you get to choose. You can set one to null, the other to null, but we've noticed that those patterns were common. Any other questions? Yes.
So you mentioned a lot of algorithms that fit pretty nicely into this framework. Have you run into any algorithms that you would like to fit nicely but don't? Like what of the ones you talk about, which are the most problematic, or what don't you support that you would like to?
With the gather apply scatter
model? Just with GraphLab in general.
So you know, I talked about the basic version of GraphLab. We've added some functionality to deal with things that don't fit so well into the abstraction. So for example, if you want to keep track of a convergence rate or you're doing a global gradient, you need to do some kind of global aggregation on top of this or have some shared parameters across machines. For example, if you're doing parameter sharing. And so that doesn't fit so neatly in the abstraction, so we have extra functionality on top to do that. The gather apply scatter model, it turns out that you can write the original GraphLab 1 abstraction in the gather apply scatter model with some loss, where in the gather you just keep accumulating state from all your neighbors. So it is as representative as the earlier one, but perhaps slightly less efficient. And we have some examples where it would be bad, and I'm happy to go through them with you. Thanks. I see a little pressure on the side here. So
we're going to catch up time.